Thank you. Thank you for having me, and thank you for coming to the talk. I know from first-hand experience that it's hard to attend too many, so I appreciate those of you who come out. So I intend to talk about streaming, which you've just heard about, and also about Arthur-Merlin, which thankfully yesterday, because of Hartmut's and Andy's talks, you've heard about too. So there's a lot that I don't need to really define for you. Okay, let me talk about a problem that I think you all know. It's a nearest neighbor search problem, and I'm going to show you in this talk an algorithm for this problem of a very unusual sort. Okay. Anyway, the problem is that you have a data set, which is a huge set of points, shown in red here, from some metric space M. And if you don't like to think of an abstract metric space, just think of these as points in Euclidean space of some high dimension. The task is to pre-process this set of points and produce a data structure, which you will then use to answer queries. So the problem comes in two phases naturally. First there's the pre-processing phase, and then there's the query phase. In the query phase, you're given a query point y, and you have to find its nearest neighbor in that data set, denoted by nn of y, x. The two important parameters here are the size of the data structure that you compute and the time you take to answer the queries. And my interesting twist is going to be that I'll think of the whole problem in a streaming setting. So the points are being streamed to you. You only have a small amount of memory, sublinear amount of memory, and therefore your data structure itself has to be sublinear in space. Okay? And I'll ignore this issue that the time has to be sublinear. I mean, it sort of naturally will follow, but concentrate on the space used by the data structure. Now, if you know anything about streaming, they should start setting off alarm bells, and you should think that this cannot be possible. It cannot be possible to do this at all, as stated. And indeed, here's a quick proof that it's not possible. So nearest neighbor is a very complicated problem. A very, very special case of this problem is when all the points are in 1D, and therefore you just have a collection of numbers. Now, if I can solve nearest neighbor, then in particular, I should be able to tell you whether the given query point actually occurs in the set of numbers that I saw before. So I have a set of numbers that I see as a stream. I have to pre-process it and remember something about it so that I can answer whether any given number appeared in the stream or not. For fairly simple information theoretic reasons, this should be very hard to do. In particular, if you think of this as a communication game where Alice holds the data structure, Alice holds the data and therefore will create the data structure, and then will communicate the contents of this data structure to Bob, who will then answer the query, then what I've set up is really an instance of the famous index problem, which is of course very hard. So any algorithm using v bits of space gives you a v-bit communication protocol. This is not possible unless v is omega n, n being the, say, the universe size. And so really there's not that much you can do. So it seems that in order to solve nearest neighbor as a data stream problem, you need some kind of help. Okay. All right. So yeah, people know who that is. I believe people know. Well, it's Arthur, right? Well, it's Arthur from one of the Monty Python movies. Anyway, okay, so Arthur-Merlin, many of you have seen the concept defined in a couple of talks, but still I'll give you my spin on it. The general setup is that you have a computationally limited entity. Classically, this would mean that you have a polynomial time algorithm, a randomized polynomial time algorithm, but you want to solve some problem that you don't believe lies in P, and so you take the help of your wizard, Merlin. The wizard is computationally arbitrarily powerful and can solve any problem, but the only issue is Arthur doesn't necessarily trust him. So there's a chance that Merlin is trying to cheat Arthur into accepting an answer that accepting some input that he should not accept. Okay, I tried to find a good picture of Merlin, but all I found was Gandalf. Yes, all right. Okay, so anyway. Traditionally, these characters are sometimes also called the verifier and the prover or helper. So I'll sometimes slip into this terminology. Now in the streaming setting, you can think of Arthur as modeling a data stream algorithm. So rather than the limitation being computational time, Arthur's limitation is that he has only a little amount of memory. Now how can Merlin help him? Well, of course, Merlin can help him by not having a limited amount of memory and therefore being able to compute anything. Now I want to put another spin on this thing before going on with my results, which is that I think in the two talks that we saw yesterday, which involved Arthur and Merlin, this was kind of an intellectual exercise to understand what the power of Arthur-Merlin models is. Well, actually, in Andy's case, he was using it to understand something else. In my case, I want to claim that there is actually something practical that Merlin can be seen as modeling. So I want to put this spin that Merlin is a proper model of what could be a cloud service, a third-party cloud service that you don't necessarily trust. Okay, so think of this model of computation. You have a lightweight, not very powerful computer that's doing your data stream processing. So you, in the modern age, you design some kind of algorithm which runs partly on your computer, but mostly perhaps on some server up in the cloud. Okay, so this data stream is being seen by you as well as the server up in the cloud. For the server in the cloud, the stream is not really a stream. It's just a piece of data because it doesn't have space limitations. It can do offline processing. But you don't necessarily want to trust that whatever answer you get from the cloud is correct. So perhaps you want to engage in a short conversation with the cloud where the cloud will convince you that the answer to your problem is so-and-so and it's correct. Okay. One last bit of pitching. Just want to say that this is you may say that modeling cloud as Merlin is perhaps a little too much because the whole point of Merlin is that he's untrustworthy. Well, our cloud service is untrustworthy. Well, you decide. I took this out of the terms of service of a well-known cloud computing service that I will not name. Okay, anyway. So, what was that?
You trust the statement?
I took it from their website. That's about as much as I trust, but anyway. Okay, anyway, fine. Let's get to the mathematical details. So this is kind of a theory that I've started building with co-authors, especially Cormode and McGregor, over a few years. And then there's another important paper by Cormode, Mitzenmacher, and Taylor, which considered interaction between Arthur and Merlin in this setup. I can give you a full history of what was done before, but I won't go into it too much because I really want to show you this algorithm. Okay, so the setup is that you have a stream consisting of m items. Each item is from a universe of size n, and m and n are both very huge, and I will kind of think of m and n as being close, let's say polynomially related, so I will not distinguish between them too much. You have an algorithm which has to process the stream using v bits of memory. This number, the letter v is for verification, so I'm using v rather than s. And then we have this helper Merlin who's also looking at the stream in parallel, and he has no memory limit. And at the end, when the stream is over, you have to answer some question about the stream, such as, say, a nearest neighbor query. At this point, Arthur will interact with Merlin using some communication protocol that we get to design. Let h be the number of bits exchanged in this communication protocol. So we wish the space used here as well as the communication used here to be much smaller than m and n, sublinear, ideally polylogarithmic. And we want the following semantics. If Merlin is honest and follows the protocol that we've designed, then Arthur must output the correct answer with high probability. On the other hand, if Merlin is dishonest, then Arthur must abort. That is to say, he must catch Merlin cheating with very high probability. Okay. All right. So this problem, point query, which is simply telling if a given stream contains a number or not. We saw that this was a very, very special case of nearest neighbor searching. I'm first going to show you a solution that says that whereas without Merlin you clearly require omega n space for trivial information theoretic reasons, with Merlin present we can design what we call a streaming interactive proof, or a SIP, with both parameters around log n. Okay? And I will show you this algorithm in some detail, and the nearest neighbor algorithm will follow as a kind of corollary of this, which seems hard to believe because this problem is a very, very special case of nearest neighbor. Nevertheless, this contains all the hardness. Okay. So yeah, so I should note that you can't hope to go much below the bound that we have. You can probably shave off the log n. I don't know how to do it, but you need log n just to store one item from the stream. So. Okay, so formally the problem is that you're given these items x1 through xm, each in n, set n, and the query is some other potential item y, and you want to know whether there exists a j with xj equals y. So does y appear in the stream? Now in the description of the protocol that is to follow, for simplicity assume that all the items x1 through xm are distinct. I don't really need that, but it'll help you understand the matter better. So I will have a certain setup, and on the next page I will have a lot more formulas coming up, but I will hopefully walk you through them and explain everything. We will first use this simple bit of notation switch where we have a mapping between integers from 1 up to n to strings, binary strings, namely their binary representations. So I'll think of n as 2 to the b, so that every integer has a b-bit representation. Okay. Now I will do all my work on some suitable finite fields. I'm going to be doing arithmetic in this finite field. I'll start off by picking b random elements in this finite field. Right? Now here's how I process the stream. I initialize an accumulator q to 0, and each time I read an item in the stream, I update my accumulator in this manner. Right? Now, one or two of you may have figured out what exactly this is doing. If you haven't yet done so, don't worry, that I'm going to explain this now. So the net effect of all these additions is, I claim, and this you can stare at this and see this is what's happening. You have evaluated a certain polynomial p at the point r1 through rb, where the polynomial is given by this formula. Okay? And I have really not done much here. I've just changed ri to zi and then written out that summation, which says that's what the accumulator computes. Okay, now what exactly is that polynomial? So this is just a recollection of what we've done so far. Notice that if you plug in 0, 1 values for z1 through zb, then this polynomial is doing something interesting. So first of all, it's a sum of a bunch of terms. Now let's look at just one of those terms, so the product inside. Now let's look at one of the factors of this product. So this xi, these xi's represent binomial, so x super j subscript I. So these represent the bits of the items that appeared in the stream. Okay, so they are binary representations of the integers that appeared in the stream. Most importantly, each xji is either 0 or 1. Now if I think of plugging in zi's as 0 or 1, then it's easy to check that this little expression in here tells you whether xi is equal to zi. So it's just a simple equality test. Therefore the product tells you whether the tuple z1 through zb is equal to the tuple x1 through xb. Okay? And therefore, in the sum, the jth term is a 1 if z is equal to xj. So this is a tuple equality. So this b tuple is equal to this b tuple. Otherwise, it's equal to 0. So it's equal to 0 if z is not equal to xj. Okay? So all this works for z being a binary string of bits. Okay? All right. So the net effect is that the sum then computes the number of times that a particular item z appears in the stream. Okay? Now, because I assume that the elements of the stream were all distinct, this count is really telling you whether the item z appeared in the stream or not. Okay? So this interpretation hopefully makes sense. It's if you plug in Boolean values, it tells you presence or absence of the numbers in the stream. But now, of course, you're free to plug in things that are not Boolean. Okay? So here's another view of what we've done so far. We had the data stream, which is a collection of integers. This collection of integers is then mapped to a collection of points in the Boolean hypercube of b dimensions. You can think of the Boolean hypercube as sitting inside this extended hypercube f to the b, right? For the finite field f that we're working on. And the net effect of that entire processing is to evaluate the polynomial that represents the stream in some manner at some random point. Okay? So this polynomial has all the information about the stream. So of course, I'm not storing the polynomial, but I'm storing its value at some particular point, right? Okay. So I've evaluated the polynomial there. In order to answer a query, so a query point is somewhere in that hypercube, I have to know if the blue query point is sitting on top of one of the black points that are actually in the stream. That's the same thing as evaluating the same polynomial p at the query point. I have already evaluated it at that random point. How can I use this information? Okay, so here's where Merlin comes into play. So I send Merlin the line through the evaluation point and the query point. It's a line in the finite, in f to the b. Okay? So it's a finite set of size exactly order of f. So this is my challenge line, and I'm saying my challenge line, pretending I'm Arthur. Okay, so suppose I'm Arthur. I'm challenging Merlin, tell me the description of that polynomial p when restricted to the line. Okay? So note, so this is coming back to something you've seen before. This is the expression for the polynomial. It is easily seen to be multilinear in the variables z1 through zb. And so if I project it on a line, then its degree will be at most b. Right? Okay. So when Arthur sends this challenge to Merlin, Merlin if he is not cheating, should be able to respond with a degree B polynomial, univariate degree B polynomial that represents P on that line lambda. Okay? So,
he hides the Ri's.
yes, he hides the
How
Ri's.
does he represent? He sends the polynomial.
Okay, good question. So how exactly does he send, he has to describe this challenge line lambda to Merlin in a way that doesn't actually reveal the Ri's. So one easy way to do this is to say that every line is some finite set, order the items in some lexicographical order, and send the first two. So 2 points uniquely determine the line, and that'll do it. And this has no information about R. Right? So that's a good point. Okay, Merlin must not know where is the place that Arthur has evaluated this polynomial. Right? We will see, the analysis will come up soon. Anyway, so if Merlin doesn't cheat, then Arthur now has a description of the polynomial as restricted to that line, and we know that answering the query amounts to evaluating the polynomial somewhere on that line, so he can go ahead and evaluate it. The query is answered, okay, so it's done.
Sorry.
Yeah.
Merlin also knows the point to be queried, right? So why does he need to? Why does Arthur need to send 2 points?
The line is determined by the point to be queried which Merlin knows, and the evaluation point which Merlin does not know. This was chosen by Arthur at random. Right?
One other point, right? Not 2 points.
Okay, fine. One other point. Sure. That will do.
At the second query, Merlin will know where these lines intersect.
Sure. So the method is good for only one query. If you wanted to do multiple queries, you have to store multiple such fingerprints or encodings or what have you. Yeah. But given that this is only logarithmic space, it's actually it's okay to do that. All right. Let's analyze this protocol. Okay, I guess some of the analysis has already started coming out in the comments. So correctness, the protocol clearly has perfect completeness. If Merlin is honest, there's no reason for any error to happen. On the other hand, if Merlin is dishonest and sends some kind of wrong polynomial, which is not actually the restriction of P to lambda, then this polynomial, being of degree B, will disagree with our polynomial, which is also of degree B, at all but B points, right? All but at most B points. Okay, so if Arthur gets unlucky, then he would have evaluated the polynomial at one of these B points of agreement, but the probability of this happening is B divided by the cardinality of the line, which is B divided by F. Okay? Now you can make this as small as you want, for example, by picking F to be around 1000 times B. This can be made less than 0.1%. Okay, so I ought to say, I realized that I forgot to write it down on the slide, that this basic setup and idea really is from a somewhat older paper of Ranra's, where his motivation was something else to do with quantum computing, I believe. But yeah. Okay. Anyway, so should have put that in there. Sorry. The other thing to analyze is the cost of this algorithm. What are we storing while processing the stream? Well, we're storing these B random points from the field. So the space taken is B times log of F. Remember that we set the field size to be 1000 B, so this is just B log B. And remember that n was 2 to the B, so B is log n, so this is just log n log log n. And the, I do not want to update right now. Is it still? Oh, somehow it's switched to a different set of slides. Sorry. You didn't see that. Oh dear, this is terrible. I don't know how I'm going. I don't know. I don't know how that went away.
Go to window in the menu and choose full screen.
Wow. Too many. Oh, okay. Thank you. Good idea. Where am I? Okay, good. Yeah, the communication. So if you look at the communication, then what Arthur sends is 2 points in F to the B. So that's order B points in the field F. And what Merlin sends back is a degree B polynomial. So that's again B coefficients in F. And so overall it's B log F again. And so it's the same log n log log n. All right? Okay, so hopefully that made sense and used several ideas that may have been familiar to you from other contexts. But we've done something very interesting, which is we've effectively solved the index problem, one-way index problem, with one-way communication but using only log n space thanks to this Merlin thing. Okay. Okay, this is just a summary of everything that we have said so far. Okay, but this only solves point query. What about nearest neighbor, right? So how on earth does this have anything to do with solving nearest neighbor? So here you'll have to imagine a few steps, but I will eventually make them a little more concrete. First, though, a discretization assumption, I need this to make the protocol work. I'm going to assume that my points are they're in some dimension d. I'm going to assume that their coordinates lie between 1 and n. And I'm also going to assume that my distance function only gives me multiples of 1 over n to the d. So this n is some kind of granularity parameter. And this is more or less true for Euclidean distance or L1 distance or so on and so forth. And if it's not exactly 1 over n to the d, but something like 1 over n squared to the d, then well, it's no big deal. The results won't change. You can just assume that there's some factor here in front of the d. It doesn't change anything. Okay, so let us consider the set B, which is all the distinct balls in this space. So all possible centers and all possible radii. Okay, that's a finite set because of this granularity assumption, right? Now, when I read my stream, which is a stream of points in X, then this generates, I will imagine in my mind, a virtual stream of balls. Okay, and here's the virtual stream. So every time I read a point X, I imagine that I'm actually seeing all the balls that contain this point. So all the balls with centers everywhere possible that contain this point. Okay. So this virtual stream is huge. Okay, fine, but it's only virtual. So imagine Arthur processing the virtual stream as if to perform point queries. Okay, so you can pretend that Arthur is seeing a stream of balls, and then he's eventually going to be able to answer membership in the stream of balls. All right. Now we are given a query point y. We want to find the nearest neighbor of y with respect to a given data set.
Is it the union of all the set of balls, one for each point?
Not the union. It is the set of balls. So each input in the stream leads to an input of millions of points in the virtual stream. The length of the virtual stream is equal to some huge number times the length of your actual stream. Yeah. So anyhow, so given a query point, Arthur will do this 3-round interaction with Merlin. So first, Merlin will say, here is the claimed nearest neighbor of your point. Now Arthur challenges Merlin to prove that this is correct, and notice that what you have to prove is that the claimed point actually appears in the given stream. So the 0 radius ball actually appears in this virtual stream. And also that this is actually the nearest neighbor, so there's nothing closer than z to y. And this can be rewritten, if you just see this, a little bit of thinking, that if you take the ball centered at z with radius slightly less than the distance, then it must not appear in this virtual stream, right? Now these are just 2-point queries, so we can solve the whole thing in space that is logarithmic in the length of this virtual stream. And thankfully, this is still order d log n, okay? So that's the small space solution. Now you may say that that's really cheating because it's a small space solution that uses an inordinate amount of time. So the work required to actually process a single point is to actually pretend that you've seen this whole virtual stream. It doesn't use a lot of space, but you have to actually add whatever you must add to your accumulator so many times, right? Now there is a way out actually, and this way out gets a little more algebraically complicated. So I won't show you the full details, but I'll give you an idea of what to do. The basic thing to observe is that we created this virtual stream, and the algorithm that I just showed you assume no form for this virtual stream, right? So it's just some random stream of balls, not random, arbitrary stream of balls. But in fact, this virtual stream has some internal structure. It arises from some metric, right? Such as, I don't know, Euclidean metric or something. Importantly, any reasonable metric comes with an efficient formula for computing it. Okay? So I can take this formula and use, write this formula algebraically, and then instead of creating a multilinear polynomial extension of the stream, so as in my point query thing, so the point query represents your stream in the form of this multilinear polynomial, right, which I was showing in the picture. Here we can instead get a higher degree extension by using this formula. Okay? So a few quick words on how to do that. So, I mean, don't concentrate too much on what the final results are, but I want to tell you the idea for constructing this extension. So let's say we have this formula phi, which takes two inputs, a description of a ball and a description of a point, and tells you whether the ball contains the point or not. Okay? In the case of, say, Euclidean metric, this would amount to computing a Euclidean distance between a given center and a given point, and comparing it to some given radius and seeing if it's less than or equal to or not. Right? The whole thing has a shallow circuit. You can then turn the circuit into a polynomial by doing this standard trick, which, for instance, is certainly used in Shamir's proof of IP equals P space, and maybe earlier. Convert AND gates to multiplication, OR gates to this thing, and your circuit turns into a polynomial. So now, our goal is to point query this vector, which has an entry at each ball, and the entry at a ball is whether or not the ball contained a given point, right? So this whole sum now becomes a sum of a bunch of polynomials. This whole polynomial has low degree because the degree of this polynomial is related to the depth of the circuit, and the circuit need not have much depth because the thing that you're computing is like just sum of squares and then some less than or equal to operation. So that's the argument. Yeah.
Arithmetic formula phi, but in the case of Euclidean thing, it is actually some real computation, right? I mean,
That's why I made this discretization assumption that the coordinates are integers. If the coordinates are integers, then the computing squares and adding is just the usual integer multiplication and addition. The only reason why I have to think about Boolean formulas at all, by the way, is because of the less than or equal to operation. I have to compare one distance to another and say that this is less than that. That's not algebraic, and this really requires a Boolean circuit. Everything else, though, is just algebraic computation. So. Okay, so that's all I wanted to say about that. Let me end with two quick. Okay, I guess I have the couple of minutes that I started late. All right, so. This connects to communication complexity, the theory of communication complexity, in the usual way, which is that data stream lower bounds come from communication complexity to lower bounds, usually. If you wanted to prove lower bounds in this model, you have to start thinking about Arthur-Merlin communication complexity, such as the kind of things that Hartmut was talking about yesterday, except that there's a slightly different twist on the Arthur-Merlin model here. Now, the data streaming algorithm naturally gives you a one-way protocol from Alice to Bob. Okay? So the communication between Alice and Bob will only be one way. On the other hand, Merlin gets to interact with Bob, so Bob represents the player who gets the tail end of the stream. So after you've seen the stream, you get to interact with Merlin in some arbitrary fashion. Okay? So we'll refer to this kind of thing as an online interactive proof protocols, or OIP, with the superscript k representing the number of rounds of communication between Bob and Merlin. OIP1 is already an interesting model because this represents Alice sending something to Bob and Merlin sending something to Bob, and then Bob deciding whether he likes the input or not, right? That's already an interesting model with some non-trivial results, okay, which I will not go into today. The protocol that I implicitly showed you for the index problem in communication is an OIP2 protocol, because Alice sends a message to Bob, and Bob sends a challenge line to Merlin, Merlin sends something back, and then the answer is given. So that's an OIP2 protocol. You can actually ask what happens as you use more and more rounds of communication between Bob and Merlin, and something very interesting happens. At least I think it's very interesting. You have separations between the classes OIP 1, 2, 3, and 4, but no further. At OIP 4, it becomes the same as OIP k for any other constant k. Okay? And anyhow, so why this happens will take too long to explain. I can do it offline. I can tell you tomorrow. Sorry, I can't tell you tomorrow. But I can tell you after tomorrow. So there's connections with the classical theory of interactive proofs, but there are subtleties. So not every theorem that you knew for classical interactive proofs, such as Goldwasser-Sipser, just goes through as it is. Okay. So anyway, which is why the collapse is at 4 and not 2, for those of you who know that very well. Okay. So in conclusion, this is the beginnings of a theory for verifiable or trustworthy cloud computing. Strictly speaking, I'm only looking at one aspect of things, which is the streaming and limited memory aspect. There's a ton of other aspects you could think of looking at. Okay, we solved nearest neighbor. I didn't say it, but there's a whole bunch of other query problems we can solve. Quick mention of a few open problems. So of course, first thing is understanding exactly what we can solve. Okay, so what was it about the structure of nearest neighbor? Can we abstract it enough and say what is the most general thing we can solve like this? But more importantly, lower bounds. We don't really have very many lower bounds, as the fourth level of this hierarchy, as I've noted before, is surprisingly powerful and contains all the other levels. And it seems to be related to AM in communication complexity, which is a famously hard thing to lower bound. So maybe we can't do that. But here's a possibly tractable question. My nearest neighbor protocol used 3 rounds of interaction. And I don't know that I can't do it in 2. I think I can't do it in 2, but I don't see how to prove it. So possibly a good problem to work on. All right, thank you.
So, one question. So I know that the model doesn't care about it, but how efficient is Merlin? So there is one step that's inefficient.
Yes. The Merlin, yeah, that's right. We wrote a few things about this in the paper, especially because we were claiming to solve nearest neighbor in some interesting model. He certainly doesn't. I mean, he certainly needs no more than polynomial time. That part is fine. He needs a lot of space. He does need to accumulate the entire. Huh? What? I think he's in polynomial time. I believe so. Yeah.
In the stream size.
In the stream size, yes, which is not very good at all. You want to be near linear time or something like this. So if you want, what's that?
Log space, right?
Log space. Merlin, no, I don't think so, because he needs to be able to extract the coefficients of the polynomial for that line. I'm not too sure that this can be done in log.
If we can do it in log space on the players to themselves, and then you would be solving in that.
Yeah, I suppose so. Yeah. Somewhere he must need more space, because otherwise he can't help solve this problem. Yeah. No, but more importantly, I don't know if you can do this in anything close to linear time. Even it may require some. I don't want to say something off the cuff, but I believe that the time taken by Merlin again relates to the size of the circuit, which represents the formula for Euclidean distance and less than. I mean, we say something about it in the paper. And I should really look at it carefully to see what we said, but.